Far beyond the calm blue edge of our skies, where sunlight fades into starlight and the silence of space stretches endlessly, something strange is stirring. 3I Atlas, once dismissed as a simple interstellar comet, is no longer behaving like one. Its path, once smooth and predictable, has begun to twist. Its speed, its spin, even its brightness flickers in ways no natural object should. Scientists are calling it an anomaly. But anomalies don't change direction with purpose. They don't slow down, pause, and then accelerate again. And they certainly don't realign themselves mid-flight, as if steering. Across observatories tonight, one unsettling question hangs in the air. If 3I/ATLAS is just a comet, why does it move like a spacecraft that knows where it's going? You've clicked on this video for a reason, because deep down you sense it too. Something out there isn't following the rules anymore. So as you settle in, tell me, where are you watching from tonight? Earth feels a little smaller when we look outward together. I am the sleepy professor, your companion through these quiet journeys, a place where we explore the universe slowly, carefully, and always with wonder. Let's drift deeper into the silence between certainty and the unknown. Chapter 1. A comet that steers itself. There's something drifting through the darkness between stars that doesn't quite behave the way it should. Something that moves with purpose, even though purpose should be impossible. Something that steers. Picture a vast ocean of night, silent, cold, infinite. Through this ocean, a traveler drifts, following invisible currents that have been charted and predicted for centuries. These currents are gravity's touch, the gentle pull of the sun and planets, predictable as clockwork, constant as mathematics itself, and yet this traveler nudges itself aside. Its name is 3I Atlas. To most, it would appear as nothing more than a faint smudge on a detector, a handful of photons arriving after a journey measured in light years. But to those who watch the sky with patient instruments and careful mathematics, this object has become a quiet mystery, one that unfolds not in dramatic revelations, but in tiny discrepancies, in numbers that refuse to line up, in a trajectory that seems to correct itself as if guided by invisible hands. The question hangs in the vacuum like morning mist. Is this truly just a comet, an ancient chunk of ice and dust, following the only path gravity allows? Or is something subtler at work? Something that makes it drift and turn with the precision we usually reserve for spacecraft? Before you imagine alien technology or interstellar probes, let's float together into calmer waters. The universe has always been stranger and more inventive than our first guesses. Nature builds mechanisms we later copy, creates engines without engineers, navigates without navigators. The answer to our mystery may not be artificial intelligence, but natural intelligence. The simple, elegant physics of ice meeting sunlight, of momentum exchanged in microscopic gasps, of forces so gentle they can barely be measured yet powerful enough to bend a trajectory across the width of the solar system. This is a story about forces that whisper rather than shout, about accelerations measured in fractions of millimeters per second, accumulated over weeks and months, until they become impossible to ignore, about the difference between what we expect to see and what we actually observe, that narrow gap where all the interesting questions live. 3I Atlas isn't behaving like a runaway spacecraft. It's not performing dramatic maneuvers or changing course with obvious intent. Instead, it's doing something far more subtle and, in its own way, more fascinating. It's drifting just slightly off the path that gravity alone would carve through space. It's nudging itself with forces we can barely detect, in patterns we're still learning to read. Imagine watching a leaf drift down a stream, and noticing, just noticing, that every so often, without wind or current to explain it, the leaf shifts a few centimeters to the left. Then again, then once more. Each shift is small, easily dismissed. But together they form a pattern They suggest that something is acting on that leaf, something the stream alone cannot explain. This is what astronomers are seeing when they plot 3I Atlas path against the predictions of gravity. The object should be here, their models say, but it's actually off by a margin so small it took months of observations to confirm, yet consistent enough that chance and error can be ruled out. Something is pushing, something is steering. The temptation, of course, is to leap immediately to the extraordinary. We've been conditioned by stories and speculation to hear spacecraft-like and imagine metal hulls, propulsion systems, perhaps even crew compartments tucked inside that distant point of light, but the cosmos rarely works that way. The extraordinary in space is usually just the ordinary, operating under conditions we haven't encountered before, or at scales where intuition fails us. So we'll resist that leap. Instead, we'll do what good science always does. We'll gather observations, we'll build models, we'll test predictions. We'll trace this mystery back through the physics of ice and sunlight, through the mechanics of rotation and sublimation, through case studies of other visitors who've puzzled us before. We'll learn what comets can do when they're far from home, how natural forces can mimic technological ones, and why just a comet is never just anything. The night sky is patient. 3I Atlas isn't going anywhere quickly. At least, not by human standards. It's giving us time to watch, to measure, to wonder. And in that wondering, we might discover something about how the universe builds its own spacecraft, its own navigation systems, its own quiet genius. So let's begin this journey together, floating through the data and the darkness, following the trail of those tiny, impossible nudges. Let's meet 3I Atlas properly, learn its name and its origins, and see what secrets it might be carrying across the light years. Because if there's one thing the universe has taught us, it's this. When something doesn't behave as expected, the explanation is rarely magic and almost never aliens. Usually it's something far better. Physics we forgot to consider. Chemistry we haven't studied. A natural process elegant enough to look designed. And that's the mystery we're here to unfold, gently and thoroughly, until the whispers in the dark resolve into words we can understand. Now that the question has been placed in the sky, let's drift closer. Every object that wanders through our solar system carries a name, not just any name, but a coded identity that tells a story to those who know how to read it. Chapter 2. Each part of that designation is a breadcrumb, a clue, a chapter in the brief history of how we discovered this visitor and what it might mean. Let's start with that curious I. In the nomenclature of the International Astronomical Union, the letter I stands for Interstellar, a word that should make us pause and feel its weight. Interstellar, between the stars. This is an object that, if the designation holds, didn't form in our cosmic neighborhood. It was born in orbit around another sun, in a planetary system we'll never see, shaped by conditions and chemistry that might be subtly or dramatically different from our own. At some point in its long history, gravitational interactions, perhaps a close pass by a planet, perhaps the slow erosion of its orbit by passing stars, ejected it from its home. It became a wanderer, drifting through the galaxy's disk, through clouds of gas and emptiness, until chance brought it close enough to our sun to be caught, briefly, in our instrument's gaze. The 3, before that, I tells us something equally profound. If confirmed, this would be the third interstellar object we've positively identified passing through our solar system, the third visitor from the cosmic ocean beyond. The first, of course, was Oumuamua, discovered in October 2017. A discovery that changed everything, that opened our eyes to the realization that interstellar objects might be far more common than we dared to hope. The second was to Borisov, found in August 2019, a more conventional-looking comet that reassured us that some things, even from other star systems, behave exactly as our theories predict. And now, 3I Atlas, a potential third chapter in this new book of knowledge. The designation is still tentative, of course. Confirmation of interstellar status requires meticulous orbit determination, requires ruling out any possibility that this object is merely a long-period comet from our own Oort cloud, stretched out on an orbit so elongated, it might as well be interstellar, but technically isn't. The line between extremely distant solar system resident and true interstellar visitor can be razor-thin when you're working with the uncertain data of faint, fast-moving objects. But let's talk about that second part of the name, Atlas. This isn't a mythological reference, though the weight of the sky is certainly involved. Atlas stands for the Asteroid Terrestrial Impact Last Alert System, a sky survey that operates multiple telescopes spread across different sites around the globe. Each telescope is relatively modest in size, nothing like the giants on mountaintops that hunt for the most distant galaxies or the faintest exoplanets. But Atlas doesn't need to be huge. What it needs is to be wide and fast. Every clear night, Atlas surveys vast swaths of sky, imaging the same patches repeatedly, looking for anything that moves or changes. Asteroids that might threaten Earth, supernova flaring in distant galaxies, variable stars pulsing through their cycles, and occasionally something utterly unexpected. A faint dot of light moving against the stars in a way that makes the automatic detection software flag it for human attention. That's how 3I Atlas was born as a name and as a mystery. Somewhere in the endless stream of data, a moving object appeared. I thought den myte som var. Something as very var. Not dramatic, not bright. Just there, where it hadn't been before, and moving in a direction that warranted a second look. The discovery was reported to the Minor Planet Center, the clearinghouse for all such findings, and astronomers around the world began turning their instruments toward those coordinates, gathering the follow-up observations needed to turn a handful of positions into an orbit, and an orbit into an understanding. Interstellar objects are special, not because they're particularly large or bright. They're usually neither. They're special because they're samples. Imagine being confined to a single island your entire life, and then one day, a piece of driftwood washes ashore, carrying seeds and insects from a land you've never seen. That driftwood is a window, a glimpse into ecosystems and climates beyond your horizon. Interstellar objects are our driftwood from other star systems, carrying information about planetary formation processes, about the chemistry of protoplanetary disks, about how common, or how rare, the conditions that led to our solar system might be in the wider galaxy. T for passing. Every measurement we make of 3I Atlas is a question asked of another stellar system. What materials went into its making? What ices condensed in the disk around that distant star? What ratio of rock to volatile, of carbon to silicon, of simple molecules to complex organics? We're reading the biography of a place we'll never visit, written in spectroscopy and light curves, in subtle accelerations and the faint glow of sublimating ice. The discovery process for such objects is always a race against time. Interstellar visitors are, by definition, not bound to our sun. And depending on their trajectory, we might have weeks, months, or, if we're very lucky, a year or two to study them before they fade back into the depths of space, too distant and too faint for even our best telescopes. This urgency shapes everything. the scramble for observing time on major telescopes, the coordination between observatories in different hemispheres to maximize coverage, the rapid analysis and publication of results so that the global community can focus its efforts efficiently. With 3i Atlas, that process is ongoing. Every new observation refines the orbit slightly, adjusts the confidence intervals, adds a pixel or two of resolution to our understanding. Some nights, clouds or moonlight or technical problems prevent observations. Other nights, the data flows in clean and clear, and the picture sharpens. This is astronomy as it's actually practiced. Patient, incremental, collaborative, and punctuated by long stretches of waiting for the sky to cooperate. But here's what makes 3i Atlas particularly intriguing in this growing catalogue of interstellar visitors. That spacecraft-like behavior we whispered about in the opening. 1i Oumuamua showed something similar, tiny accelerations that couldn't be explained by gravity alone. 2i Borisov, by contrast, behaved exactly as a comet should, with visible outgassing and a predictable trajectory. So which category does 3i Atlas fall into? Is it the reassuring comet following the rules we've spent centuries learning? Or is it the puzzle, the anomaly, the one that forces us to expand our understanding? The answer, as we'll see, is woven through the data, in the positions measured night after night, in the brightness fluctuations, in the absence or presence of a faint coma, in those subtle residuals that refuse to vanish, no matter how carefully we account for the sun's gravity and the planet's gentle tugs. 3i Atlas is more than a catalogue entry. It's a conversation with the universe, written in mathematics and light, asking us to listen carefully and think deeply about what it means for a comet to steer itself, and whether just a comet has ever been a simple thing at all, with a name and a place in the catalogue. Let's see how astronomers turn faint traces of light into precise paths in space. Chapter 3. Turning dots into orbits. There's a certain magic in astronomy that never quite fades. No matter how technical the work becomes, the magic of turning light into knowledge. A handful of photons, weary from their journey across millions or billions of miles, strike a detector. They create a tiny electronic signal, a whisper in the data stream. And from that whisper, if you're patient and precise, you can reconstruct an entire story. Where an object is, where it's been, where it's going, and sometimes even what it's made of. This is the art and science of astrometry, the careful measurement of positions in the sky. For 3i Atlas, as for every object that moves against the fixed stars, the process begins with those measurements: right ascension and declination, the celestial equivalent of longitude and latitude, recorded with a timestamp precise to the second. Each observation is a single point, a coordinate pair, a moment frozen in the object's journey, but a single point tells you almost nothing. You can't distinguish a nearby asteroid from a distant comet, from a speck of dust on your detector. You need more points. You need the object to move, to trace a path, to reveal its motion against the unchanging background of stars. And so the observations accumulate. Tonight, 3i Atlas is here. Tomorrow night, there. A week later, somewhere else entirely. Each measurement carries uncertainty. The atmosphere blurs and distorts. The detector has its own noise and limitations. The object itself might be faint, its light barely distinguishable from the background glow of the sky. So every position comes wrapped in error bars, margins of uncertainty that say the object is probably here, within this small patch of sky, but we can't be absolutely certain. This is where the Minor Planet Center enters the picture. Astronomers from around the world report their observations to this central hub, positions, times, magnitudes, uncertainties. The MPCs collects these reports, validates them, and makes them available to the community. It's a system that's been refined over more than a century of asteroid and comet tracking, and it works beautifully because it's built on trust, standardization, and the shared recognition that no single observatory can track every object all the time. With enough observations in hand, the real work begins: orbit fitting. This is where mathematics meets physics, where you try to find the path through space, the orbit that best explains all those observed positions. It's an optimization problem, elegant in its simplicity, but often brutal in its complexity. You start with an initial guess, a rough orbit based on just a few observations. Then you refine it, adjusting the parameters. Orbital elements, like eccentricity, inclination, perihelion distance, until the predicted positions match the observed ones as closely as possible. The quality of an orbit fit is measured by the residuals, the differences between where your model says the object should be and where it was actually observed. Small residuals mean a good fit. Large residuals mean something is wrong. Either the observations are bad, the model is incomplete, or the object isn't following a simple gravitational path. For most asteroids and comets, a purely gravitational model works beautifully. You account for the Sun's gravity, add in the subtle pulls of Jupiter and Saturn and the other planets, but early on in the observation of 3I Atlas, something curious began to appear in those residuals. They weren't shrinking as fast as they should. Even with the best gravitational model, even accounting for every planet and every known force, there were systematic differences, small but persistent, consistent but unexplained. This is the signature we've been gently circling, the hint that something beyond gravity is acting on this object. Photometry runs parallel to astrometry in this process. While positions tell you where an object is, brightness tells you, well, many things. How large it might be, how reflective its surface is, whether it's rotating, whether it's shedding material, whether it's fragmenting or outbursting or changing in ways that speak to its physical nature. Absolute magnitude, designated H in the literature, is a standardized measure of how bright an object would appear if placed at a specific distance and phase angle. It's a way to compare apples to apples, to say this comet is intrinsically brighter than that asteroid, even though they're at different distances from both the Sun and Earth. Colors, too, matter. Blue light versus red light measured through different filters can hint at composition. Is the surface covered in fresh ice? Organic rich dust? Bare rock? Different materials reflect and absorb different wavelengths, painting subtle rainbows in the data that spectrometers and filter wheels can decode. Light curves, brightness changing over time, reveal rotation. As 3I Atlas spins, different facets catch the sunlight at different angles, creating a rhythmic brightening and dimming. The period of that rhythm tells you how fast it's rotating. The amplitude, how much the brightness changes, hints at the object's shape. A perfect sphere shows no variation. An elongated object, tumbling end over end, creates dramatic brightness swings. All of this data, astrometry, colors, light curves, feeds into a growing understanding of 3I Atlas as a physical object, not just a moving dot. But understanding is always provisional in science. Early orbits are rough sketches, drawn with sparse data and large uncertainties. As weeks pass and observations accumulate, those sketches sharpen into detailed blueprints. The error ellipses, the regions of uncertainty around the predicted position, shrink. The orbital elements stabilize. Confidence grows. Yet for 3I Atlas, even as the orbit stabilized, the whisper of those residuals remained. Something small but real was nudging the object away from a purely gravitational path. The measurements were too good, the observations too consistent, the pattern too clear to dismiss as noise or error, and that's when spacecraft-like stopped being a quirky description and started being a problem that demanded explanation. A problem that would lead us into the physics of ice and sunlight, of jets and torques, of forces too gentle to see, but powerful enough to steer. And yet, even the best-fit orbits sometimes whisper that something else is at work. Chapter 4. Why spacecraft-like? What the data actually show. Let's linger for a moment on that phrase, spacecraft-like. It's provocative, almost dramatic, the kind of description that invites speculation and headlines. But what does it actually mean, stripped of connotation and hype? Translated into the sober language of orbital mechanics, it means this. When you model 3I Atlas trajectory using only the gravitational forces of the Sun and planets, the same forces that govern everything from Mercury's tight orbit to the distant drift of View cloud comets, the model doesn't quite work. The observations don't match the predictions. The object appears where it shouldn't be, arrives when it shouldn't arrive, drifts in directions gravity alone cannot explain. These discrepancies are called residuals, and they are the bread and butter of orbit determination. Residuals are simply the difference between observed position and predicted position. In a perfect world with perfect measurements and a complete model, residuals would be zero. In the real world, they're never zero. There's always noise, always measurement uncertainty, always some small error. But residuals should be random, scattering evenly around zero with no pattern or trend. For 3I Atlas, the residuals aren't random. They're systematic. They show a pattern, a consistent drift in a particular direction, accumulating over time in a way that randomness cannot explain. This is the hallmark of a missing force. Something acting on the object that your model hasn't included. In orbital mechanics, when purely gravitational models fail to explain observations, we turn to non-gravitational acceleration. These are forces beyond gravity. Friction from gas or dust in space, radiation pressure from sunlight, and most commonly for comets, recoil from outgassing, the rocket effect of vaporizing ice, pushing the nucleus in the opposite direction. The key insight is this. Non-gravitational accelerations, though tiny, are cumulative. Imagine pushing a shopping cart with one finger. The push is gentle, barely perceptible in the moment, but keep pushing, minute after minute, and the cart will roll across the parking lot. That's what's happening with 3I Atlas. Some force, or combination of forces, is giving it a gentle, continuous push, and over weeks and months, that push adds up to a measurable change in trajectory. To see this in action, astronomers add non-gravitational terms to their orbit models. They introduce new parameters representing accelerations in various directions, radial, toward, or away from the Sun, transverse along the direction of motion, and normal perpendicular to the orbital plane. They refit the orbit with these extra degrees of freedom, and watch what happens to the residuals. If the non-gravitational accelerations are real, the residuals will shrink dramatically. The model will suddenly match the observations far better than before, and the values of those new parameters, the magnitude and direction of the extra forces, will stabilize, becoming well-determined rather than arbitrary. This is exactly what happened with 3I Atlas. Add a small transverse acceleration, a push in the direction of motion or opposite to it, and the orbit fit improves dramatically. The systematic drift in the residuals vanishes. The predictions align with the observations. The object's path, once puzzling, now makes sense within a framework that includes something beyond gravity. And here's where the spacecraft-like comparison comes in. When spacecraft perform trajectory correction maneuvers, tiny burns of their thrusters to adjust course. The signature in tracking data looks very similar. A small, consistent acceleration, often transverse to the orbit, accumulating over time to produce a measurable shift in trajectory. The signature is so similar that if you didn't know you were looking at a comet, you might genuinely wonder if someone had installed engines. But, of course, there are no engines on 3I Atlas. No fuel tanks, no thrusters. No mission planners uploading commands from mission control. The spacecraft-like behavior is entirely natural. It's just that nature has found a way to mimic the effects of propulsion using nothing but ice, sunlight, and the vacuum of space. The key difference lies in intention and predictability. Spacecraft maneuvers are planned, executed at specific times for specific purposes, designed to achieve precise outcomes. The accelerations from comet outgassing, by contrast, are stochastic and driven by thermal processes. They depend on where the sun is, which patches of the surface are illuminated, what ices are present and at what depths, how fast the nucleus is rotating. They're not random, they follow physical laws, but they're not planned either. They're emergent, arising from the interplay of heat, sublimation, rotation, and structure. This is why comets often show non-gravitational accelerations. It's not new, it's not mysterious in the sense of being unknown. What makes 3I Atlas interesting is the how and the why in this specific case. Is the acceleration consistent with typical comet outgassing? Is it unusually strong or weak for an object of this size and distance from the Sun? Is there visible activity, a coma, or tail? Or is the outgassing somehow invisible to our instruments? These questions matter because they constrain the physics. Strong acceleration with no visible coma suggests unusual composition. Perhaps ices that sublimate at lower temperatures or produce minimal dust. Weak acceleration with clear activity suggests a typical comet that just happens to be faint or far away. The magnitude, direction, and timing of the non-gravitational forces become clues, pieces of a puzzle that, when assembled, reveal the nature of the object. It's worth emphasizing that spacecraft-like is a metaphor, a shorthand, a way to make the technical more accessible. It's not a claim. No serious astronomer is suggesting that 3I Atlas is artificial. The language is simply acknowledging that the observable behavior, small, consistent accelerations altering the trajectory, resembles what we see in spacecraft tracking, even though the underlying cause is entirely different. And that, in a way, is the deeper wonder. Nature doesn't need engineers to build propulsion systems. Give it ice, give it sunlight, give it time, and it will create jets and plumes and gentle rocket effects all on its own. The universe is a master of using simple ingredients to produce complex, counterintuitive outcomes. A comet steering itself through the solar system without intention or design is just one example among many. So when we say 3I Atlas behaves like a spacecraft, what we're really saying is this: it moves in a way that tells us gravity isn't the whole story. There are other forces at play, subtle and persistent, writing their signatures into the orbit. Our job now is to identify those forces, understand their sources, and see what they reveal about this distant visitor's composition, structure, and history. The data have spoken. The residuals have whispered their secret. Something is pushing 3I Atlas, and that something is worth understanding. To understand the nudges, we need to know what a comet is, and how it breathes under sunlight. Chapter 5. Comets 101. Snow, dust, and sunlight. To understand why comets can steer themselves, we need to understand what a comet truly is. Not the glowing spectacle we see in photographs, but the cold, dark reality at the heart of it all. Strip away the coma, the tail, the shimmering halo of gas and dust that makes comets famous, and you're left with something surprisingly humble. A nucleus, a dirty snowball, a lump of ancient ice and rock, typically just a few kilometers across. It's darker than coal, often as black as asphalt, absorbing most of the sunlight that touches it. And it's old, profoundly old. A relic from the solar system's birth, preserved in the deep freeze of the outer reaches for 4.5 billion years. The nucleus is where everything begins. It's a mixture, a cosmic slush of water ice, frozen carbon dioxide, carbon monoxide, methane, ammonia, and a host of more complex organic molecules. Mixed throughout are grains of dust, silicates, carbon compounds, perhaps even tiny crystals of metal, all held together in a matrix so porous and fragile, it's more like a snowbank than a solid rock. The density is low, often less than that of water, which means that despite being frozen, a comet nucleus is actually full of empty space, riddled with voids and pockets where vacuum and ice meet in a delicate balance. For most of its existence, a comet nucleus is inert. Out in the Oort cloud, or the Kuiper belt, far from the sun's warmth, temperatures hover near absolute zero. Nothing sublimates, nothing moves. The nucleus is dormant, a frozen time capsule drifting through the dark. But bring it closer to the sun, close enough that sunlight begins to warm the surface, and everything changes. This is where the magic begins, where physics transforms a dead chunk of ice into a living, breathing comet. The process is called sublimation, the direct transition of ice from solid to gas, bypassing the liquid phase entirely. On Earth, you see this when dry ice, frozen coal, turns to vapor without melting. In space, water ice does the same thing, though it requires more heat. Carbon dioxide sublimes at greater distances, carbon monoxide even farther out. Each ice has its own threshold temperature, its own distance from the sun, where warmth finally penetrates the cold. As sublimation begins, gas molecules escape from the surface, streaming upward into the vacuum. For mat barujens sajuv. They carry with them dust grains, particles that were trapped in the ice, now freed by the evaporation. This mixture of gas and dust expands outward, forming a cloud around the nucleus called the coma. The coma can grow enormous, sometimes larger than Jupiter, even though the solid nucleus at its heart remains tiny. The coma glows faintly, illuminated by sunlight. Some of the glow is reflected light off the dust. Some is fluorescence, ultraviolet sunlight energizing gas molecules, causing them to emit visible light at specific wavelengths. Observers on Earth see these emission lines in spectra. The greenish glow of diatomic carbon, the cyan of cyanogen, the violet of ionized carbon monoxide. Sa modestie. The Silai, far, shon, the. Each line is a fingerprint, a clue to what ices are vaporizing, what chemistry is happening in the expanding cloud. As the gas and dust stream away from the nucleus, the solar wind, a constant flow of charged particles from the sun, begins to interact with them. Ions are swept backward, away from the sun, forming a long, straight tail that can stretch for millions of kilometers. Dust, pushed more gently by radiation pressure, forms a separate curved tail that traces the comet's orbit. Together, these tails give comets their iconic appearance, the sweeping brush strokes across the night sky that have inspired awe and fear for millennia. But the tails are just the visible consequence of a deeper process. What matters for our mystery? What explains the spacecraft-like behavior of 3I Atlas and others? Is what's happening at the surface of the nucleus, where sublimation and structure meet. The comet doesn't have a rocket engine, but it has something functionally similar. Patches of surface ejecting gas at speeds of hundreds of meters per second, creating thrust entirely by accident, entirely through the physics of sublimation. This is the rocket effect, and it's both elegant and complicated. Elegant because the basic idea is so simple. Outgassing equals thrust. Complicated because the details, where the gas comes from, how fast it's moving, in what direction at what times, depend on a web of interconnected factors: surface composition, rotation state, thermal properties, structural porosity, and the angle of sunlight. Let's start with the simplest case. A spherical comet nucleus, uniformly covered in water ice, rotating steadily on its axis. As the sun rises over a patch of surface, that patch warms. The temperature climbs above the sublimation threshold for water, around 200 Kelvin or so, and ice begins to vaporize. Gas escapes perpendicular to the surface, which means, on average, it's ejected radially away from the comet. The recoil force therefore points radially inward. To the surface orbiters, sa, the nachkazades, far from us. But wait, if the force points inward toward the center of the comet, it doesn't create any net thrust on the nucleus as a whole. Radial forces symmetrically distributed cancel out. To get a net effect, you need asymmetry, and asymmetry is exactly what real comets provide. For real comet nuclei are not spherical. They're potato-shaped, dumbbell-shaped, sometimes fragmented and barely holding together. Active regions are not uniformly distributed. They're localized patches, often near the equator, where sunlight is strongest, or in depressions where fresh ice has been recently exposed. As the comet rotates, these active patches turn into and out of sunlight, creating a pulsing pattern of outgassing, jets that switch on and off with the rotation, creating forces that don't cancel, that push the nucleus in specific directions. The direction of the thrust depends on the geometry. If most of the active area is on one hemisphere, the recoil will push the comet preferentially in the opposite direction. If jets are concentrated near the subsolar point, the spot directly facing the sun, the thrust will have a radial component plus whatever vector comes from the local surface. Normal. Complex shapes create complex torques, and then there's thermal lag. Ice doesn't respond instantly to sunlight. It takes time for heat to conduct into the subsurface, time for temperatures to rise, time for sublimation to ramp up. This means that peak outgassing doesn't happen at local noon. It happens in the afternoon, when the surface has had time to absorb and store heat. For a rotating nucleus, this lag means that jets turn on after the subsolar point has passed, creating an asymmetry in both timing and direction. Think of it like this. If the comet rotates prograde, in the same sense as its orbit, and jets activate in the afternoon, the thrust will have a transverse component, either speeding up or slowing down the comet's orbital motion. Speed up, and the orbit's semi-major axis increases. The comet drifts outward. Slow down, and it drifts inward. Either way, the purely gravitational prediction fails, and non-gravitational accelerations appear in the orbit fits. The magnitude of the thrust depends on the mass loss rate and the velocity of the ejected gas. Water vapor sublimates at a few hundred meters per second. Carbon dioxide, lighter and more volatile, moves faster. The thrust is proportional to the product of mass flow and velocity, a relationship rocket engineers would recognize immediately. More gas, faster gas, stronger thrust. But here's the catch. We don't always see the gas. Sublimation can happen at very low rates, especially far from the sun or with unusual ice compositions. Carbon monoxide, for example, sublimates at much greater distances than water, where the comet is still too faint and far for easy observation. If 3I Atlas is outgassing CO rather than water, it might be producing thrust without producing a visible coma, because CO doesn't drag much dust and doesn't fluoresce as brightly. This leads to one of the central puzzles of spacecraft-like comets, the invisible thrust. You see the acceleration in the orbit, but you don't see the plume. It's like watching a boat drift across a lake without seeing the oars. You know something is pushing, but the mechanism is hidden. Another complication. Rotation isn't always simple. Some comets spin around a single axis, like a top. The Mote Zeussenses, farthest thee me knows. The others tumble chaotically, with rotation axes that wobble and precess. Tumbling comets produce jets whose directions swing wildly over time, creating accelerations that vary in magnitude and direction in ways that are fiendishly difficult to model. The orbit fits become exercises in frustration with non-gravitational parameters that refuse to stabilize. And then there are torques. Outgassing doesn't just push the nucleus, it can also spin it up or spin it down. If jets are not aligned with the center of mass, they exert torque, changing the rotation rate. Faster rotation brings different surface patches into sunlight more quickly, altering the pattern of activity. Slower rotation means longer days, deeper heating, different thermal cycles. The comet's spin and its activity are coupled in a feedback loop, each influencing the other. Some comets spin up so much that they literally come apart, fragmenting under centrifugal stress. Others spin down toward a stable state. The torques are yet another way that sublimation shapes, not just the orbit, but the physical evolution of the nucleus. So when we talk about the rocket effect, we're not talking about a simple, steady push. We're talking about a complex interplay of surface physics, rotation dynamics, thermal lag, composition, and geometry, all conspiring to create accelerations that look, in the cold language of orbit residuals, like someone is steering. Nature, it turns out, is an excellent engineer, even without intention. But what if we don't see a coma at all? Can a comet still push itself? Let's float into that puzzle. Cracks, vents, and structural weaknesses allow gas to escape from deeper layers, creating jets that emerge through the lag without producing a widespread coma. The outgassing becomes localized, concentrated, and potentially invisible unless you're looking at exactly the right spot at exactly the right time. And then there's the question of detection limits. Every telescope, every detector, every observing campaign has a threshold, a minimum brightness below which objects simply cannot be seen. For faint, distant comets, that threshold can be uncomfortably high. A coma might be there, just faint enough to blend into the noise of the sky background, visible only to the largest telescopes or the longest exposures. Upper limits on coma detection. Statements like, "We searched for a coma and found none brighter than X," are valuable data points, but they're not the same as proving no coma exists. They prove only that any coma present is fainter than X, which still allows for considerable activity. Spectroscopy is the gold standard for detecting invisible comae. Even if you can't see the glow in an image, you can search for emission lines, the fingerprints of specific molecules fluorescing in sunlight. Cyanogen CN is a favorite target because it's relatively easy to detect and is a good proxy for overall activity. Hydroxyl O, a product of water dissociation, is another. Carbon dioxide ions show up in the ultraviolet and near-infrared. But spectroscopy requires time, large apertures, and favorable conditions. For a faint, fast-moving object like 3I Atlas, securing enough telescope time to conduct deep spectroscopic searches is a constant challenge. Observing windows are limited, weather intervenes. Competing programs vie for the same instruments. Sometimes you get the data, sometimes you don't, and you're left with upper limits and tantalizing hints rather than definitive answers. Upper limits, though, are still constraints. If you search for CN and find none down to a very sensitive threshold, you can calculate the maximum amount of CN that could be present, which translates into a maximum water production rate, which in turn constrains the strength of water-driven outgassing. If the observed non-gravitational acceleration is stronger than water can plausibly produce at that production rate, it suggests another ice, CO2, or something even more exotic, is doing the work. This is the detective work of invisible Comet, ruling out possibilities, narrowing the field, piecing together constraints from non-detections and upper limits until the truth emerges from the gaps. For 3I Atlas, the invisible coma problem is front and center. If it's thrusting like a comet, where's the coma? Is it too faint, too dust-poor, dominated by ices that hide at optical wavelengths? Or is something else entirely? Radiation pressure, perhaps, doing the pushing? We'll explore that alternative next. But for now, let the question linger. Can a comet breathe without showing its breath? And if so, how would we ever know? Sunlight offers another invisible hand as well. Soft pressure that can subtly sail an object. Chapter 8. Sunlight's Gentle Hand. Radiation Pressure. 1200 words. There's a force acting on 3I Atlas that has nothing to do with ice or outgassing, nothing to do with chemistry or sublimation. It's older than planets, simpler than gravity, and it arrives on every beam of light that crosses the solar system. It's called radiation pressure, and though it sounds esoteric, the principle is beautifully straightforward. Light carries momentum. When photons, tiny packets of electromagnetic energy, strike a surface, they transfer that momentum, exerting a force. For everyday objects on Earth, this force is vanishingly small, utterly negligible, lost in the noise of wind and friction and gravity. Radiation pressure, by contrast, follows an inverse square law, proportional to 1 over distance squared, the same as the intensity of sunlight itself. If the observed acceleration tracks more closely with the inverse square curve than with sublimation, radiation pressure is the likely culprit. It's worth distinguishing radiation pressure from the solar wind, which is often confused with it. The solar wind is a stream of charged particles, protons, electrons, ions, flowing outward from the sun's corona. It does exert pressure, but on different targets. Ionized gas, plasma, magnetic fields. Frosteladids bars, For solid objects like comet nuclei, solar wind pressure is negligible compared to radiation pressure. The photon wind, not the particle wind, is what matters here. There's also a subtler effect called the Yarkovsky effect, which applies to rotating objects. As a surface absorbs sunlight and heats up, it re-radiates that energy as infrared light. If the object is rotating, the hot afternoon side radiates more than the cool morning side, creating an asymmetry in the emitted photon momentum. This imbalance produces a tiny thrust, either speeding up or slowing down the object depending on the direction of rotation. For asteroids, The Yarkovsky effect is well documented and important for long-term orbit evolution. For comets, it's usually overshadowed by outgassing, but for inactive or weakly active objects, it can become significant. Radiation pressure, then, is not a single effect, but a family of related phenomena. Direct photon momentum, thermal re-radiation, albedo-driven asymmetries, all stemming from the fundamental fact that light carries momentum in space, is a place where even the gentlest push can accumulate into water. Rose, Frada, Rudizenke. Something profound. For 3I Atlas, radiation pressure remains a possibility, a hypothesis on the table, alongside outgassing and other mechanisms. If the object is unusually low density, if it's a fragment rather than a coherent nucleus, if it's not visibly outgassing, then maybe, just maybe, it's sailing on sunlight, drifting through space with photons as its only engine. The data, as always, will decide. Observations of brightness, color, and how the acceleration varies with distance will constrain the area-to-mass ratio, test the radiation pressure model, and reveal whether 3I Atlas is a comet, a fragment, or something in between. Now imagine those pushes modulated by spin, like a slow celestial dance that reshapes direction over time. Chapter 9. Spin, Seasons, and the Dance of Torques. Everything in space is spinning. Planets, moons, asteroids, comets. Nothing sits still. Nothing hovers motionless. Rotation is the inheritance of formation, the result of collisions and accretion, and the conservation of angular momentum as clouds of gas and dust collapsed into solid bodies. And rotation, once begun, shapes everything that follows. For comets, spin is not just a curiosity. It's a fundamental control on activity, on where and when outgassing happens, on the direction and strength of the rocket effect, and ultimately on how the orbit evolves over time. A comet's rotation is the clock that governs its breathing, the rhythm that determines which patches of surface see sunlight and which remain in cold shadow. Let's begin with the simplest case. A comet rotating steadily around a single axis like a planet. This is called principal axis rotation, and it's the default assumption in most models. The comet spins at a constant rate, let's say once every few hours, and the spin axis points in a fixed direction relative to the stars. As the comet orbits the sun, different latitudes experience different amounts of sunlight, creating seasons just like on Earth. Near the equator, day and night alternate with each rotation. Patches of surface heat up in sunlight, sublimate, and then cool down in darkness. The cycle is regular, predictable. Near the poles, the situation is more extreme. Depending on the season, a pole might be in constant sunlight for months, or constant darkness for months. Polar regions, when illuminated, can become the most active areas on the entire nucleus because they receive continuous heating without the relief of night. This seasonal variation creates changes in the pattern of outgassing over the course of an orbit. Early in the approach to the Sun, one hemisphere might dominate the activity. Post-perihelion, the other hemisphere might take over. The direction of the net thrust, the vector sum of all the jets, rotates and shifts, sometimes dramatically, as the seasons progress. But real comets rarely cooperate with the simple picture. Many comets are not in principal axis rotation. They're tumbling, wobbling, precessing, spinning in complex ways that involve multiple axes and chaotic dynamics. This happens because comets are not perfect spheres, not even close. The simple vive reasons of what the versions. They're irregularly shaped, with mass distributed unevenly, and when they're outgassing asymmetrically, The jets exert torques that can destabilize the rotation. Torque is simply a force applied off-center, creating a twist. If a jet fires from a location that's not aligned with the center of mass, it doesn't just push the nucleus, it also spins it. And because the active regions change with rotation and season, the torques are not constant. They vary in magnitude and direction, feeding energy into the rotational motion in ways that can excite wobbles, slow down or speed up the spin, or even flip the spin axis over time. Some comets spin up so rapidly that they can't hold together. Centrifugal force. Technically, the apparent force felt in the rotating frame exceeds the weak internal strength of the nucleus, and the comet simply comes apart, splitting into fragments that drift slowly away from each other. We've seen this happen multiple times, most spectacularly with comets like 73 P-Schwarzmann Watchman 3, which disintegrated into dozens of pieces as it rounded the Sun. Other comets spin down, losing angular momentum to the torques from outgassing until they settle into slow, stable rotation. However, with Bui von Mo, VB Fofenyi. The process can take decades or centuries, but eventually the most irregular spinners find equilibrium, aligning their spin axes with the principal moment of inertia, the axis around which rotation is most stable. Then there's thermal lag, a concept we touched on earlier, but worth revisiting in detail. Sunlight doesn't instantly heat the surface to its maximum temperature. It takes time for heat to conduct into the subsurface, for thermal energy to accumulate, for the temperature to rise to the point where sublimation kicks in. This creates a delay between local noon, when the sun is highest, and peak activity, which might occur hours later in the local afternoon. For a rotating comet, this thermal lag has a profound consequence. The direction of maximum outgassing is not aligned with the subsolar point. Instead, it's shifted by the lag angle, offset in the direction of rotation. This offset creates an asymmetry in the thrust, a transverse component that can either speed up or slow down the comet's orbital motion, depending on whether the rotation is prograde or retrograde. Prograde rotation means the nucleus spins in the same direction as it orbits, like Earth spinning west to east while orbiting the Sun counterclockwise as seen from above the North Pole. Retrograde rotation means the opposite. Thermal lag in a prograde rotator tends to produce a transverse thrust in the direction of motion, acting like a gentle accelerator pedal, pushing the comet into a slightly higher orbit. In a retrograde rotator, the effect is reversed. The thrust opposes the motion, acting like a brake. This is why the Marsden model, which we'll describe in detail soon, includes transverse as well as radial components. The transverse acceleration captures the effects of thermal lag and rotational modulation, translating complex surface physics into a single parameter that orbit fitters can measure and constrain. And then there are long-term effects like YORP, the Yarkovsky-O'Keefe-Radzievsky effect, a mouthful of a name for a subtle but important process. YORP is a torque generated by the asymmetric re-radiation of absorbed sunlight. As different parts of an irregular object heat up and cool down, they emit infrared photons in different directions at different times. The net effect is a slow, steady torque that can spin the object up or slow it down over thousands of years. For asteroids, YORP has been directly measured and confirmed. For comets, it's usually swamped by the much stronger torques from outgassing jets. But for inactive or weakly active comets, or for fragments like 3i Atlas might be. Yorp could become relevant, adding another layer to the already complex interplay of forces shaping the orbit and the spin. The dance of torques and rotation is one of feedback loops. Spin determines which patches are active, which jets fire. Jets exert torques, changing the spin. Changed spin alters the activity pattern. Altered activity changes the torques. It's a coupled system, dynamic and evolving, never quite settling into a static equilibrium. For observers trying to model this, the complexity can be overwhelming. You need to know the shape of the nucleus, the distribution of active regions, the thermal properties of the surface, the rotation state. And all of these are difficult to measure for a faint, distant object. Often, you end up with degenerate solutions, multiple combinations of parameters that fit the data equally well, leaving ambiguity about what's really happening. But that ambiguity is not failure. It's an invitation to gather more data, to watch longer, to measure more carefully. Each observation, each light curve, each astrometric position, each spectroscopic upper limit adds a constraint, narrows the possibilities, brings the true solution into sharper focus. For 3i Atlas, understanding the spin and the torques is crucial to understanding the spacecraft-like behavior. For tar, CD, each savats. Is it a steady spinner with predictable activity? A chaotic tumbler with erratic jets? A fragment barely holding together, shedding pieces as it goes? The answer is written in the light curves, the rotation periods, the subtle shifts in brightness and position that patient observers are collecting night after night. We've seen this dance before, in a famous visitor. Let's softly revisit Oumuamua. Chapter 10. Oumuamua Revisited, a familiar mystery, 1,300 words. In October 2017, a telescope on Haleakala in Hawaii spotted something that would change our understanding of what passes through our solar system. At first, it seemed unremarkable. Another faint dot, moving against the background stars, flagged by automated detection software as a potential near-Earth asteroid. But as observations accumulated and an orbit was calculated, astronomers realized they were looking at something unprecedented, an object on a trajectory that came from interstellar space. It was given the name Oumuamua, a Hawaiian word meaning scout, or first distant messenger, a fitting designation for humanity's first confirmed interstellar visitor. And like 3i Atlas after it, Oumuamua refused to behave as gravity alone would predict. The discovery trajectory of Oumuamua was electric with urgency. The object was already on its way out of the solar system when it was spotted, racing away from the sun at more than 26 kilometers per second. Observing windows were measured in weeks, not months. Every major telescope that could be pointed at, it was pressed into service. Optical surveys, infrared telescopes, radio dishes, space-based observatories. Data poured in, but time was running out. By early 2018, Oumuamua had faded below the detection limits of even the largest telescopes, disappearing back into the darkness between stars, leaving behind more questions than answers. The most perplexing observation came from careful astrometry. When Marco Miccioli and his team analyzed the trajectory using data from multiple observatories, they found the same signature we've been discussing: non-gravitational acceleration. Oumuamua was not following a purely gravitational path. Something was pushing it, gently but persistently, creating a small but unmistakable deviation, predominantly in the radial direction away from the sun. The magnitude of the acceleration was tiny, measured in millimeters per second squared, accumulated over weeks. But it was real, statistically significant, impossible to dismiss as noise or systematic error. Something was acting on Oumuamua besides gravity. The obvious explanation would be cometary outgassing, the rocket effect we've explored in detail. Heat from the sun vaporizes ice. Gas jets create thrust. The object accelerates. Simple, natural, observed in countless comets. Except for one glaring problem. Oumuamua showed no visible coma, no dust tail, no spectroscopic signature of gas. No evidence whatsoever of the activity that should accompany outgassing strong enough to produce the observed acceleration. This was the invisible coma problem taken to its extreme. Not just faint activity, but apparently zero activity, despite clear dynamical evidence that something was pushing. The scientific community responded with a cascade of hypotheses, each attempting to reconcile the acceleration with the lack of visible outgassing. Some ideas were conservative, invoking subtle physics within the bounds of known comet behavior. Others ventured into more speculative territory, proposing mechanisms rarely or never observed in solar system objects. One leading hypothesis suggested outgassing of unusual volatiles, ices that sublimate without producing much visible material. Carbon monoxide and nitrogen ice, for instance, vaporize at lower temperatures than water and produce minimal dust. If Oumuamua's surface was dominated by these supervolatiles rather than water ice, it could have been outgassing vigorously without creating a detectable coma. The gas would be invisible at optical wavelengths, difficult to detect spectroscopically from Earth, and would carry little to no dust. Another idea proposed that Oumuamua might be composed of hydrogen ice, essentially frozen molecular hydrogen. This is an exotic possibility, requiring formation in extremely cold environments. But hydrogen ice sublimates at very low temperatures and produces gas that's essentially transparent. A hydrogen iceberg tumbling through space would thrust without glowing, leaving no optical signature at all. The hypothesis was elegant but controversial, requiring special formation conditions and raising questions about how such an object could survive the journey through interstellar space without evaporating completely. Then there was the possibility that Oumuamua wasn't a solid nucleus at all, but a low-density, highly porous fragment, essentially a cosmic dust bunny, held together by little more than weak cohesion. With an extremely high area-to-mass ratio, such an object would be strongly affected by radiation pressure from sunlight. The acceleration would be purely photon-driven, requiring no outgassing whatsoever. To test this, researchers modeled the shape and density needed to match the observed acceleration via radiation pressure alone. The results were unusual. Oumuamua would need to be extraordinarily flat and thin, shaped more like a pancake or a disc, perhaps only tens of meters thick, but hundreds of meters across. Alternatively, it might be extremely elongated, needle-shaped, tumbling end over end. Either geometry could provide the necessary area-to-mass ratio, but both seemed physically unlikely for a natural object, raising eyebrows and fueling speculation. Light curves, brightness variations over time, showed that Oumuamua was indeed rotating, with a period of around 8 hours, and that its brightness varied by a factor of 10 or more. This indicated an elongated shape, consistent with the needle hypothesis, though not definitively proving it. for Asing. The object could also be a contact binary, two lobes barely touching, or some other irregular configuration. Spectroscopically, Oumuamua appeared reddish, similar to many Kuiper belt objects and some comets. This color suggested a surface rich in organic compounds, possibly tholins, complex molecules formed by irradiation of simpler ices over long time scales. The reddish hue was consistent with an ancient surface that had spent eons in interstellar space, bombarded by cosmic rays and slowly altered by radiation. But no spectral features of gas or dust were detected, despite deep searches. Upper limits on water production were tight enough to rule out water-driven outgassing as the sole explanation for the acceleration. If water was responsible, it would have needed to be sublimating at rates that should have been easily visible, and it simply wasn't. The debate around Oumuamua grew intense, spilling into public discourse and media coverage. Some proposals ventured into the realm of the extraordinary. Suggestions that Oumuamua might be an artificial object, perhaps a light sail from another civilization, drifting through the galaxy either by design or as derelict debris. These ideas, championed by a small number of researchers, garnered significant attention but remained deeply controversial, lacking the evidence needed to overcome the principle that extraordinary claims require extraordinary proof. Most of the scientific community settled on more conservative interpretations: unusual but natural outgassing, radiation pressure on a low-density fragment, or some combination of effects not yet fully understood. The lesson was clear. Spacecraft-like behavior does not imply spacecraft. Or Tanokuza's Meisendeisnen. Ver Sanan Deilses. Nature is inventive, and interstellar objects, shaped by environments we've never sampled, may behave in ways that challenge our intuitions without requiring artificial origins. What Oumuamua taught us, above all, was humility. It showed that interstellar visitors are not just exotic versions of familiar comets and asteroids. They carry with them the signatures of alien chemistries, alien formation histories, alien physical processes. They push the boundaries of our models and force us to expand the range of possibilities we're willing to entertain. For 3i Atlas, Oumuamua is both a cautionary tale and a roadmap. The mystery of non-gravitational accelerations without visible Comet is not new. The tension between observation and explanation is not unique. And the path forward: more data, better models, patient analysis. The same one we walked with Oumuamua, even if we never reached a fully satisfying resolution. But there's another interstellar visitor worth remembering. One that behaved exactly as expected, and reminded us that not every mystery needs to be mysterious. Chapter 11. If Oumuamua was the strange visitor that challenged our assumptions, 2i Borisov was the reassuring one that confirmed them. Discovered in August 2019 by Crimean amateur astronomer Gennady Borisov. This object was quickly recognized as interstellar based on its hyperbolic orbit, a trajectory that brought it from beyond the solar system and would eventually carry it back out into the depths of space. But unlike Oumuamua, 2i Borisov looked exactly like a comet should. From the very first observations, it displayed a clear, unambiguous coma, a fuzzy halo of gas and dust surrounding the nucleus. As it approached the sun, the coma grew brighter and more extensive, developing a faint tail that stretched away from the sun in the classic cometary fashion. Spectroscopy revealed familiar emission lines, CN, C2, the signatures of molecules like cyanogen and hydroxyl, that are produced when water ice sublimates and fragments under ultraviolet sunlight. For astronomers who had spent 2 years puzzling over Oumuamua's strangeness, 2I Borisov was a gift. A reminder that interstellar space is not so alien that it produces only anomalies. Comets from other star systems can be, and apparently often are, quite similar to comets from our own. The trajectory of 2I Borisov was more favorable than Oumuamua's. It was discovered earlier in its path through the inner solar system, giving observers months to study it rather than mere weeks. Telescopes around the world tracked it continuously, building up detailed light curves, multi-wavelength observations, and high-resolution imaging. Space-based telescopes, like Hubble, captured sharp images showing the coma structure and the faint nucleus at its heart. One of the most important results from 2I Borisov was the measurement of its composition. Spectroscopic analysis revealed abundances of various molecules: water, carbon monoxide, carbon dioxide, and others, that could be compared directly to comets from the Oort cloud and Kuiper belt. The surprise was that there was no surprise. 2I Borisov's composition was broadly consistent with solar system comets, particularly those formed in the outer regions. This was profound. It suggested that the chemistry of planet formation around other stars, at least the star system where Borisov originated, is similar to our own. The same ices condense. The same volatiles get incorporated into comet nuclei. The same physical processes govern how these icy bodies evolve and behave. For, to use star Jews one Negius, in other words, the Sun's planetary system is not unique. The building blocks we see here exist elsewhere, shaped by similar physics and chemistry. There were some intriguing differences, of course. Borisov's co-abundance relative to water was somewhat higher than typical solar system comets, suggesting it formed in a colder part of its birth system or retained volatiles more efficiently. Its dust production was robust, creating a photogenic coma and tail that made it easy to observe even with modest telescopes. And critically, Borisov's orbit showed the expected non-gravitational accelerations from outgassing. The signature was clear, consistent with standard comet models, and entirely explained by the visible activity. There was no mystery, no invisible thrust, no spacecraft-like anomaly, just a comet behaving as comets do, sublimating, thrusting, and steering itself gently along the modified trajectory. This normalcy was, in its way, just as valuable as Oumuamua's strangeness. It established a baseline, a reference point for what typical interstellar comets might look like. If most visitors from other star systems resemble Borisov, icy, active, compositionally familiar, then we can begin to build a statistical understanding of interstellar populations. We can ask questions like, what fraction of interstellar objects are comets versus asteroids? How common are icy bodies ejected from other planetary systems? What does the distribution of compositions tell us about planet formation across the galaxy? Borisov also demonstrated that our detection systems work. The comet was discovered by a dedicated amateur using a modest telescope. Proof that interstellar objects bright enough to show cometary activity are within reach of ground-based surveys. As survey telescopes like LSST, the Vera Rubin Observatory, come online in the coming years, The discovery rate for such objects is expected to soar. We might see dozens or even hundreds of interstellar visitors per year, building a statistical sample large enough to answer questions that single objects like Oumuamua and Borisov can only hint at. There's a certain comfort in 2I Borisov's ordinariness. It reminds us that the universe, for all its vastness and strangeness, operates by consistent rules. Physics and chemistry work the same way in other star systems. Comets form, evolve, and behave in predictable ways, whether they're orbiting our sun or passing through after being ejected from a system light years away. But that comfort doesn't diminish the importance of the anomalies. Oumuamua, and now potentially 3I Atlas, represent the edge cases. The objects that don't fit neatly into our categories, that challenge our models, that force us to think harder and look deeper. These outliers are not failures of science, they're opportunities. They're the friction that sharpens understanding, the puzzles that drive progress. So, as we consider 3I Atlas and its spacecraft-like behavior, we hold both examples in mind. Borisov shows us what to expect from most interstellar comets. Oumuamua shows us that expectations can be subverted, that nature has tricks we haven't anticipated. And 3I Atlas, somewhere between the two, invites us to determine which category it belongs to, or whether it's carving out a new one entirely. With both extremes in mind, we can compare comets to actual spacecraft, carefully and calmly. Chapter 12. Do comets navigate? Comparing to spacecraft, 1,200 words, let's perform a thought experiment. Imagine you're a flight engineer monitoring the trajectory of a spacecraft. Perhaps a probe on its way to Mars, or a satellite adjusting its orbit around Earth. You watch the telemetry, tracking position and velocity with precision instruments, and then you notice something. The spacecraft is not quite where your predictions say it should be. It's drifted slightly off course, in a consistent direction, by an amount that can't be explained by gravitational forces alone. Your immediate thought would be, someone fired the thrusters. A trajectory correction maneuver, a TCM, was executed burning fuel to adjust the velocity and nudge the spacecraft onto a better path. This is routine, expected plan. Spacecraft don't fly perfect trajectories. They need periodic corrections to account for modeling uncertainties, gravitational perturbations, and mission requirements. Now imagine you're an astronomer tracking a comet. You observe its position night after night, fitting an orbit, calculating where it should appear next. And then you notice the comet is not quite where your gravitational model predicts. It's drifted slightly off course in a consistent direction by an amount that can't be explained by the sun and planets alone. Your immediate thought would be, outgassing. The comet is sublimating, jets are creating thrust, and the rocket effect is altering the trajectory. This too is routine, expected, natural. Comets don't fly perfect gravitational trajectories when they're active. They steer themselves through the simple physics of ice vaporizing under sunlight. The signatures in both cases are remarkably similar. A small, persistent acceleration. A deviation from the predicted path. A need to add extra terms to the model to match observations. If you stripped away all context, removed the knowledge of what you were tracking, you might not be able to tell them apart based solely on the orbital data. But context matters immensely. Spacecraft maneuvers are planned, deliberate, executed at specific times for specific reasons. Mission controllers decide when to fire the thrusters, for how long, in which direction. The maneuvers are scheduled, uploaded as commands, monitored in real time. Intent and control define every action.
Comet outgassing, by contrast, is driven entirely by physics.
There are no decisions, no plans, no commands. Sunlight heats the surface. Ice sublimates when temperatures cross a threshold. Gas escapes through whatever vents or cracks exist. Jets fire wherever active regions happen to be located, at times dictated by the rotation and the thermal lag and the solar distance. It's deterministic but not designed. It follows rules but has no goals. Yet the outcomes, those small, cumulative velocity changes, can appear almost indistinguishable in the data. This is why the term spacecraft-like has gained currency. Not because anyone seriously believes comets are artificial, but because the dynamical signature, the pattern visible in the residuals and the orbit fits, mimics that of human-made objects undergoing powered flight. Let's look at the details more closely. A typical spacecraft TCM might produce a delta V, a change in velocity, measured in meters per second, executed in a single burn lasting minutes or hours. The acceleration during the burn is relatively high, perhaps thousandths or hundredths of a meter per second squared, concentrated in a brief interval. Comet outgassing produces much smaller accelerations, millionths or billionths of a meter per second squared, but they're continuous or quasi-continuous, lasting for days, weeks, or months. The cumulative delta V can add up to meters per second over an entire orbit, comparable to a modest TCM, but the process is spread out in time rather than concentrated. Another difference is directionality. Spacecraft TCM are typically designed to produce specific vector changes, radial, transverse, normal, or some combination, optimized for the mission's needs. Comet jets, controlled only by the geometry of active regions and the rotation state, produce whatever vectors those conditions happen to create. They might be predominantly radial, or transverse, or normal, or all three, depending on where the jets are located and when they fire. There's also predictability. For a spacecraft, future maneuvers are known in advance, or can be planned based on trajectory requirements. For a comet, future accelerations are inherently uncertain because they depend on activity levels that change with distance, season, outbursts, fragmentation events, and other variables that are difficult to predict. Yet, despite these differences, the fact remains, when you add non-gravitational accelerations to a comet's orbit model, the mathematics is nearly identical to modeling spacecraft maneuvers. The Marsden parameters, which we'll explore soon, are fundamentally the same as the delta V terms spacecraft navigators use. The algorithms that fit orbits to observations, the least squares optimizations, the covariance matrices. These tools work equally well for natural and artificial objects because the underlying dynamics, however different in origin, produce similar observable effects. This convergence is not coincidental. It reflects a deeper truth. Momentum is momentum, force is force, acceleration is acceleration regardless of source. Whether thrust comes from a chemical rocket or a sublimating ice patch, whether it's controlled by computers or by thermodynamics, the motion it produces obeys Newton's laws in exactly the same way. There's a philosophical dimension here worth contemplating quietly. Humanity spent millennia dreaming of flight, of controlling our motion through space, of navigating with precision. We built engines, designed spacecraft, invented mission control, and all along, comets were doing something functionally similar, steering themselves through the solar system, adjusting their paths, responding dynamically to external forces. They don't navigate in the sense of having intent or agency, but they do navigate in the sense of altering their trajectories through active processes
responding to changing conditions, following paths that are not purely ballistic.
It's navigation without a navigator, control without a controller, emergence rather than engineering. This is why spacecraft-like is such a useful metaphor. It acknowledges the functional similarity while not implying artificial origin. It allows us to describe comet behavior in language that's intuitive and vivid without making extraordinary claims, and it sets up the framework for the next step. Turning those qualitative descriptions into quantitative models. Transforming the comet is pushing itself into precise equations with measurable parameters that can be tested, refined, and used to predict future behavior. That's where the Marsden model comes in, a simple but powerful framework for translating subtle nudges into physics. To model those tiny nudges, astronomers use a simple but powerful framework. Chapter 13. Turning residuals into physics, the Marsden model, 1300 words. Science has a way of taking complex, messy phenomena and distilling them into elegant frameworks. Mathematical structures that capture the essential behavior without drowning in every microscopic detail. For comet non-gravitational forces, that framework is called the Marsden model, named after Brian Marsden, who pioneered its use in the 1960s and 70s. The beauty of the Marsden model is its simplicity. Instead of trying to model every individual jet, every patch of active surface, every thermal lag and rotation effect, it reduces the entire problem to just a few parameters, 3 acceleration components, and a distance-dependent function that describes how activity changes as the comet approaches. 3 Sunzay, Tambavade B, Barminzis, Sir, or recedes from the sun. Let's unpack that gently, piece by piece. First, the acceleration component. The model assumes that the non-gravitational force on the comet can be decomposed into 3 perpendicular directions, defined relative to the comet's orbit. Radial A1. The acceleration component pointing directly away from or toward the sun. This captures the effect of jets that fire sunward or anti-sunward, driven by dayside heating. For most comets, A1 is positive away from the sun, because outgassing naturally occurs on the sunlit hemisphere, creating thrust that pushes the nucleus outward. Transverse A2. The acceleration component along the direction of orbital motion or opposite to it. This captures the effects of thermal lag and rotational asymmetry. If jets fire predominantly in the afternoon due to thermal lag, and the comet rotates prograde, A2 will be positive, speeding up the orbit. If the rotation is retrograde, A2 might be negative, slowing down. Normal A3. The acceleration component perpendicular to the orbital plane. D Fermansis Bias fault of Orocos Enote. This is usually the smallest of the 3, arising from asymmetries in the distribution of active regions with respect to the equator. For many comets, A3 is close to 0 or poorly constrained because the out-of-plane accelerations are subtle and require very precise astrometry to detect. These 3 components, A1, A2, A3, are the heart of the model. Their parameters to be fit, determined by comparing observed positions to model predictions and adjusting until the residuals are minimized. Each has units of acceleration, typically expressed in astronomical units per day squared, or UD2, a unit that feels strange but is conventional in celestial mechanics. But acceleration alone isn't enough. Comets don't thrust at a constant rate. Their activity changes with distance from the sun. Water ice sublimates vigorously when the comet is near perihelion, close to the sun's warmth,
and tapers off dramatically as the comet recedes into the cold outer solar system. To capture this behavior, the Marsden model includes a function called gr, where r is the distance from the Sun. The standard form of gr is based on water-ice sublimation and looks like this. gr equals r0, rm times 1 plus rr0n, 1 plus 1k. Don't worry about the details of that expression. What matters is that gr peaks near some characteristic distance, r0, typically around 2.80 for water, and drops off steeply at larger distances. The exponents m, n, and k control the shape of the curve. How quickly activity ramps up as the comet approaches, how sharply it peaks, how fast it declines. For water-driven comets, the standard model uses m approximately 2.15 and n approximately 5.93, values that match laboratory measurements of water sublimation rates at different temperatures. But not all comets are dominated by water. Value water fastnar. 4 to 4th bud loud 4. Some, rich in Co or Co2, become active at much greater distances where water ice is still frozen. For these, a different gr function, one that peaks farther from the Sun, is needed. This flexibility is key by fitting not just A1, A2, A3, but also the parameters of gr. If the distance dependence doesn't match any simple sublimation law, that might indicate a complex mix of ices, or episodic outbursts, or fragmentation event. One more subtlety. The Marsden model includes an asymmetry parameter to account for the fact that comets often behave differently before and after perihelion. Pre-perihelion, the surface might be covered with fresh, volatile, rich ice that sublimates readily. Post-perihelion, after repeated heating, a lag deposit of dust may have accumulated, insulating the surface and reducing activity. The asymmetry parameter lets the model adjust the strength of gr separately for the inbound and outbound legs of the orbit. When you put it all together, A1, A2, A3, the gr function, and the asymmetry, you have a compact, powerful description of non-gravitational forces that can be fit to astrometric observations using standard least squares technique. The computer iterates, adjusting the parameters until the predicted positions match the observed ones as closely as possible. And out comes a set of best fit values with uncertainties and covariances. These fitted parameters are not just abstract numbers, they're physical clues. A large A2 relative to A1 suggests strong thermal lag and rotational effects. A large A3 suggests an unusual distribution of active regions, perhaps polar jets. A distance dependence that deviates from the water ice standard suggests exotic compositions or unusual thermal properties. DG most rydazis brustlutitans. For 3i Atlas, applying the Marsden model is a critical step. Does the observed spacecraft-like acceleration fit neatly into the framework of comet outgassing? Are the A1, A2, A3 values consistent with known comets, or do they stand out as anomalous? Does the distance dependence match water, Co, Co2, or something else entirely? Or does the model fail to converge, leaving residuals that refuse to shrink, even after adding non-gravitational terms? A hint that something other than outgassing might be responsible. This is the translation from observation to understanding. The residuals, those small differences between where 3i Atlas is and where gravity says it should be, are the raw data. The Marsden model is the Rosetta Stone, converting those residuals into statements about jets, ices, rotation, and thermal processes. It's a framework built on decades of experience with solar system comets, tested on hundreds of objects, refined and validated through missions that visited comets up close and measured their outgassing directly. And now we're applying it to interstellar visitors, objects that might have formed under different conditions, around different stars with chemistries and structures we've never encountered. Will the model work? Will the physics of comets be universal enough that tools developed for solar system objects can explain 3I Atlas? Or will this visitor require new terms, new functions, new frameworks? The data, as always, will tell us. And as the observations accumulate, the Marsden parameters will sharpen, the uncertainties will shrink, and the story of 3I Atlas, its composition, its history, its nature, will emerge from the mathematics. With tools in hand, let's map out the likeliest stories that could explain 3I Atlas behavior. Stijververbeurder meetypes. Chapter 14. What is 3I Atlas likely doing? A scenario tree, 1300 words. Now we arrive at the heart of the mystery. What is actually causing 3I Atlas to behave like a spacecraft? We've gathered the tools: astrometry, photometry, the Marsden model, radiation pressure calculations. We've studied the case histories, Oumuamua's anomaly, Borisov's normalcy. We've explored the physics, outgassing, sublimation, thermal lag, spin, porosity, and photon pressure. And photon pressure, Warmonzusens, for UVG. I agree, form the monogen. Now it's time to assemble these pieces into a coherent framework. A scenario tree, a branching map of possibilities, each with its own predictions and testable consequences. Let's walk through the most plausible explanations calmly and systematically, seeing where each path leads. Scenario 1. Low-level COCO, 2 outgassing with minimal dust. This is perhaps the most conservative explanation, the one that requires the fewest exotic assumptions. The idea is simple. 3I Atlas is a comet, actively outgassing, but the ice driving the activity is not water. Instead, it's dominated by more volatile species, carbon monoxide or carbon dioxide, that sublimate at greater distances from the sun where water remains frozen. CO and CO2 are lighter than water, and when they sublimate, they don't entrain as much dust. The result is a gas-rich but dust-poor outflow, plumes that produce thrust but don't scatter much visible light. The coma, if present at all, would be faint and diffuse, potentially below the detection thresholds of optical surveys. Spectroscopically, CO is challenging to detect from the ground, because its strongest lines fall in the infrared, in wavelength regions obscured by Earth's atmosphere. CO2 is similarly elusive, unless you have access to space-based instruments or specific narrow-band filters. So the absence of a visible coma doesn't rule out significant outgassing. It just means the outgassing is invisible to conventional observations. Predictions for this scenario. The Marsden model should fit well with a GR function appropriate for CO or CO2 sublimation, peaking at 510 or more, rather than 2.80 for water, infrared spectroscopy, especially from space telescopes like JWST, should detect molecular emission lines if the outgassing is strong enough. Light curves should show periodic variations consistent with rotation, but no dramatic outbursts unless new vents open. The A2 transverse. Acceleration should correlate with solar distance and rotation state, matching predictions from thermal lag models. Scenario 2. Radiation pressure on a low-density fragment. This scenario abandons outgassing entirely and attributes the acceleration to sunlight. The idea is that 3I Atlas is not a coherent nucleus, but a low-density shard, a piece of a larger body that fragmented at some point in its history, perhaps during ejection from its home system or during a previous perihelion passage. If the fragment is fluffy enough, density comparable to aerogel, more void than solid, its area-to-mass ratio becomes large enough that radiation pressure from sunlight produces measurable acceleration.
No outgassing required. Just photons bouncing off, or being absorbed by a surface with almost no inertia to resist the push.
This scenario explains the lack of a visible coma perfectly. There is no coma because there's no activity. The object is inert, dead, drifting on a sunbeam.
Predictions for this scenario. The acceleration should follow an inverse square law with solar distance proportional to 1r2, matching the intensity of sunlight rather than a sublimation law curve. The magnitude of the acceleration constrains the area-to-mass ratio, which in turn constrains the object's size and density. For 3I Atlas, matching the observed acceleration would likely require a density well below 100 kgm², less dense than styrofoam. Styrofoam v. For version war days.
Light curves should be consistent with an irregular, possibly elongated shape rotating steadily. No spectroscopic signs of gas or dust should be detectable, even in deep observations or at sensitive wavelengths.
Scenario 3.
Anisotropic jets modulated by tumbling. Here we return to outgassing, but with a twist. The comet is not rotating smoothly around a single axis. Instead, it's tumbling chaotically, with rotation axes that wobble and precess. Active regions fire jets that swing wildly in direction as the nucleus tumbles, creating accelerations that vary in both magnitude and orientation over time. Tumbling can arise naturally from asymmetric outgassing torques, especially in small, weak bodies that can't resist the angular momentum imparted by jets. If 3I Atlas is tumbling, the non-gravitational forces become time variable, making orbit fitting more difficult and potentially leaving larger residuals even after adding Marsden terms.
Predictions for this scenario.
Light curves should show complex, non-periodic variations. Brightness changes that don't repeat on a simple cycle, indicating non-principal axis rotation. The Marsden model might fit poorly, with large residuals remaining even after optimization, because the model assumes steady or smoothly varying acceleration. More sophisticated models that include time-dependent accelerations would be needed to match the data. If the tumbling can be characterized rotation period, precession rate, etc., it might be possible to predict future accelerations and test the model with subsequent observations.
Scenario 4.
Episodic outbursts or fragmentation comets sometimes undergo sudden brightening events called outbursts, where a patch of fresh ice is suddenly exposed, perhaps by a cliff collapse, a subsurface pocket venting explosively, or a chunk of the nucleus breaking away.
These outbursts produce spikes in activity, surges of gas and dust, and corresponding jumps in the non-gravitational acceleration. If 3I Atlas has experienced one or more outbursts, the acceleration might not be smooth or continuous. Instead, it could show step-like changes, periods of higher or lower thrust, separated by relatively abrupt transitions. Fragmentation, the nucleus splitting into two or more pieces, would produce similar signatures, with each fragment experiencing slightly different forces and drifting apart over time. Or does D or one shape.
Predictions for this scenario. Light curves should show sudden brightness, increases corresponding to outburst events, followed by gradual fading as the ejected material disperses. Astrometric residuals might show discontinuities, jumps in position that can't be explained by smooth accelerations, requiring impulsive delta V terms in the orbit fit. High-resolution imaging HST, large ground-based telescopes with adaptive optics, might resolve multiple components if fragmentation has occurred. The acceleration components A1, A2, A3 might change values before and after an outburst, reflecting changes in the active region distribution or mass of the nucleus. Cross-scenario tests. Fortunately, many of these scenarios make distinct testable predictions that allow us to narrow the possibilities. Distance dependence of acceleration. Outgassing scenarios predict sublimation law curves. Radiation pressure predicts inverse square. So, measuring how the acceleration changes with solar distance is perhaps the single most powerful discriminator. Spectroscopy. Detection of gas emission lines confirms outgassing and identifies the active ice species. Non-detections, combined with sensitive upper limits, constrain outgassing rates and favor radiation pressure or very unusual volatiles. Photometry and light curves. Rotation periods, brightness variations and color changes provide clues about shape, activity, and surface properties. Sotometer fotitet bort. Två louds märkt. G. Complex or changing light curves favor tumbling or outbursts. Simple, stable curves favor steady rotation or inert fragments. High-resolution imaging, resolving the nucleus or detecting a coma, directly confirms structure and activity. Non-detections constrain size and surface brightness, indirectly constraining density and albedo. Each observation adds a constraint, a piece of evidence that favors some scenarios and disfavors others. The process is iterative. Propose scenarios, predict observations, collect data, revise scenarios. Slowly, the tree of possibilities is pruned, branches eliminated, until ideally only one, or a small handful, remain consistent with all the evidence. For 3i Atlas, this process is ongoing. The data are still being gathered, the models still being refined. But the framework is in place, the questions well posed, the tests designed. Whatever the answer turns out to be, the path to finding it is clear. Sometimes, however, spacecraft-like behavior really is spacecraft, or space junk. Let's gently separate those threads. First, if it's truly on an interstellar trajectory, barycentric energy greater than zero, coming from outside the solar system, then it can't be terrestrial debris, which is gravitationally bound to the Sun. Second, the distances involved are, but the 2020 SO episode is a reminder to stay cautious and check assumptions. The universe has a way of surprising us, not always with exotic phenomena, but sometimes with mundane ones masquerading as exotic. Ruling out prosaic explanations is not a formality. It's a necessary step in any scientific investigation. There's also a subtler point here about detection bias. Space debris is often discovered precisely because it passes close to Earth, where our detection capabilities are strongest. Interstellar objects, by contrast, are usually discovered farther out, moving fast, fading quickly. The observational circumstances themselves provide clues. Where was it first seen? How fast was it moving? What direction was it going? For 3i Atlas, the discovery circumstances. Detection by a wide field survey, faint and distant. moving on a trajectory consistent with an interstellar origin. All point away from space junk and toward a natural object, but the comparison is instructive nonetheless. Or, de Titan Tassens, te zien, te ze dicht vast.
It shows that spacecraft-like accelerations are not unique to natural interstellar visitors. Artificial objects can produce them too, through radiation pressure and structural characteristics that mimic exotic natural phenomena. The key, as always, is evidence. Follow the data, test the hypotheses, and don't assume the most exciting explanation is correct just because it's exciting. Sometimes the answer is space junk. Sometimes it's a comet. Sometimes it's something new. Let the observations, not the narrative, guide the conclusion. To truly know, you gather data together across the globe and across wavelength. Chapter 16. The Worldwide Chase. How we observe a visitor. 1,200 words. Astronomy, at its best, is a global collaboration. A symphony of observers, instruments, and intellects working in concert across continents and time zones, united by curiosity and the shared recognition that no single telescope, no single team can capture the full picture alone. For an object like 3i Atlas, faint, fast-moving, potentially transient, the observing campaign is both race and marathon. Every clear night is an opportunity. Vaardied, cirkelende af. Unuts, thar, sol, the bezels, far. Every cloudy night is a loss. Coordination becomes essential. Data sharing becomes critical, and the community comes together in ways that transcend borders and institutions. Let's tour the worldwide infrastructure that makes such campaigns possible, starting with the ground-based facilities that form the backbone of Comet and asteroid tracking. Ground-based optical telescopes. The workhorses of Comet observation are the 2 to 10 meter class telescopes scattered across the world's best observing sites. These include legendary names, Keck and Subaru on Mauna Kea, the Very Large Telescope in Chile's Atacama Desert, Gemini North and South, spanning both hemispheres, the Gran Telescopio Canarias in the Atlantic, and many others. Each brings unique capabilities. Large apertures collect more light, allowing observations of fainter objects, or longer integrations for spectroscopy. Wide-field capabilities allow imaging of extended Comet, or searching for fragmentation. Adaptive optics systems correct for atmospheric turbulence, sharpening images to near-space telescope quality. For 3i Atlas, photometry is the bread and butter, measuring brightness over time to construct light curves, determine rotation periods, monitor for outbursts. Multi-band photometry, observing through different filters that isolate specific wavelengths, reveals colors that hint at composition and surface properties. Spectroscopy is the gold standard. A spectrum spreads the object's light into a rainbow, revealing emission lines or absorption features that identify specific molecules and ions. For comets, the key targets are CN, C2, C3, O, all traces of water and carbon-rich chemistry, plus rarer species like NH2, CH, and ions like Co+ and Co. Obtaining a spectrum of a faint, distant comet is challenging. The object is moving relative to background stars, requiring non-sidereal tracking. The telescope must follow the comet's motion precisely, or the spectrum will smear and blur. Integration times are long, sometimes hours, to accumulate enough photons for analysis. And wavelength calibration is critical. Comet emission lines are narrow, and identifying them correctly requires precision. Space-based observations, ground-based telescopes are powerful, but Earth's atmosphere is a veil.
It absorbs ultraviolet and infrared light, blurs images, adds noise, and scatters light from cities and the moon. Space-based observatories bypass these limitations, offering clarity and access to wavelengths invisible from the ground. The Hubble Space Telescope, though decades old, remains a premier tool for imaging faint comets. Its sharp optics resolve fine structure, dust jets, coma morphology, even the nucleus itself if the comet is close enough and inactive enough. For 3I Atlas, Hubble observations could search for faint Comet below ground-based detection limits, constrain the nucleus size, or detect fragmentation. The James Webb Space Telescope brings unprecedented infrared sensitivity. Its spectrographs can detect molecules like CO2, H2O, and organics with exquisite detail, even at faint flux levels. For 3I Atlas, JWST could definitively identify or rule out specific ice species, measure production rates, and probe thermal properties through infrared continuum measurements. Or FUZI says UFAV, SA, radio and millimeter observatories. Gas molecules emit not just visible light, but also radio waves at specific frequencies corresponding to rotational transitions. Carbon monoxide CO, for instance, has bright lines in the millimeter band around 115 GHz and higher frequencies. 4. Those of Rosenzer, the Atacama, large millimeter submillimeter array ALMA in Chile, is perfectly suited to detect these lines, mapping the distribution and velocity of gas in the coma with stunning resolution. ALMA observations can reveal asymmetric outgassing, rotating gas structures, and even measure isotopic ratios, 2C3C, for example, that carry information about the comet's formation environment. For a suspected interstellar visitor, isotopes are gold. They're a direct comparison to solar system norms, revealing whether the object's chemistry is exotic or familiar. Hydrogen cyanide, HCN, methanol CH3O, and formaldehyde H2CO are other radio-bright molecules that trace different chemical pathways. Detecting a suite of these molecules builds a compositional profile, a chemical fingerprint of the comet's heritage. Eine Hormittel is born bar, verbreit, da. Narrowband comet filters. Many observatories employ specialized filters designed specifically for comet observation. These are narrowband filters centered on the wavelengths of key emission lines. CN at 388 NAD, C2 at 514 nAmu, C3 at 406 nAmu, O at 308 NAB. By imaging through these filters and comparing to continuum filters that isolate the dust scattered light from dust, LADAs 3 La, thus war, measure production rates and monitor temporal variations in activity. For 3I Atlas, systematic narrowband imaging would reveal whether any gas is present, even at levels too faint to produce a visible coma in broadband images. Coordinated cadence and non-sidereal tracking. Observing a moving object requires coordination, not just between telescopes, but also careful scheduling within each observing run. Light curves need temporal coverage, observations spaced hours apart to sample the rotation cycle, then repeated over days and weeks to track long-term changes. Astrometry requires precision, positions measured to fractions of an arcsecond, with timestamps accurate to seconds. These measurements flow into the minor planet center, where they're combined with data from other observers to refine the orbit. Non-sidereal tracking, guiding the telescope to follow the comet's motion across the sky. is essential for spectroscopy and deep imaging.
The stars will streak, but the comet will remain sharp, allowing long exposures that reveal faint features.
Upper limits as data. Not every observation leads to a detection, and that's okay.
Upper limits, statements like, "We observed for X hours and detected no coma brighter than Y," are valuable constraints. They bound the parameter space, ruling out strong activity, setting maximum production rates for gas species, and forcing models to explain the acceleration with weaker or more exotic mechanisms. In many ways, upper limits are as important as detections.
They narrow the possibilities, eliminate scenarios, and guide future observations toward the most promising targets and technique.
Data sharing and archives.
The data collected from this worldwide effort flow into public archives. The Planetary Data System, the European Space Agency's archives, observatory-specific databases. This openness is foundational to modern astronomy.
Independent researchers can reanalyze data, test alternative models, discover details the original observers missed. Science progresses faster when data are shared freely. For 3i Atlas, every image, every spectrum, every photometry table is a puzzle piece. Individually, they're snapshots, limited by weather and instrument availability. Together, they form a mosaic, a comprehensive portrait of a distant visitor, assembled from the combined efforts of dozens of teams using dozens of facilities. This is how we observe interstellar visitors. With patience, collaboration, and the recognition that the universe is generous with its mysteries but demands rigor and openness in return. As we refine observations, ideas mature into plans. Can we someday meet an interstellar visitor up close? Chapter 17, Catching the Next One. Interceptors and Rapid Missions, 1,300 words. There's a dream that's been quietly growing in the mission planning offices and conference rooms of space agencies around the world. The dream of not just observing an interstellar visitor from afar, but meeting one up close. Of sending a spacecraft to intercept, to orbit, to sample, to touch. Transforming photons and spectra into physical encounters, turning distant mysteries into tangible, analyzable reality. It's an audacious dream. Interstellar objects move fast. Typically, 20-40 kilometers per second relative to the Sun. Speeds that dwarf the velocities of even our fastest spacecraft. They're discovered late, often when already on their way out of the solar system, leaving narrow windows measured in months or at best a year or two before they fade beyond reach, and they're unpredictable. We can't schedule a mission to launch in 2035 to meet an object we won't discover until 2033. Yet, despite these challenges, the dream is not fantasy. Engineers and mission designers have been working through the constraints, developing concepts and strategies that could, with the right preparation and a bit of luck, allow humanity to catch the next Oumuamua, or 2i Borisov, or 3i Atlas. ESA Comet Interceptor. The most advanced concept currently is the European Space Agency's Comet Interceptor mission, selected in 2019 and scheduled for launch in the late 2020s. The strategy is elegant. Instead of chasing a specific target, Comet Interceptor will park itself at a gravitationally stable location, the Sun-Earth Lagrange point L2, about 1.5 million kilometers from Earth, and wait. L2 is a parking spot in space, where the gravitational pulls of the Sun and Earth balance, allowing a spacecraft to remain in place with minimal fuel. It's the same location where the James Webb Space Telescope orbits, maintaining its position while observing the universe. For Comet Interceptor, L2 serves as a perfect ambush point,
far enough from Earth to avoid too much gravitational binding, close enough to communicate easily, and positioned to strike outward toward an incoming target once one is identified. The mission carries 3 spacecraft, a main probe and 2 smaller subprobes. Once a suitable target is discovered and confirmed, a pristine comet from the Oort cloud, or ideally an interstellar visitor, the mission springs into action. The spacecraft leave L2, perform trajectory maneuvers to intercept, and then split apart days before arrival. Each probe flies past the target from a different angle, imaging, measuring, sampling, capturing data from multiple perspectives simultaneously. Simultaneous from mobile to thesaisgever, voorreed does it the thosses, the saws, for before. Far. The main probe might fly through the coma, sampling gas and dust directly. Together, they provide a 3-dimensional portrait of a comet in action, far richer than any single flyby could achieve. The beauty of this strategy is flexibility. The mission doesn't commit to a specific target years in advance. It waits ready until the best opportunity arises. If an interstellar object is discovered with favorable geometry, Comet Interceptor could be our first spacecraft to touch something from another star system. Project Lyra and Fast Intercept concepts. While Comet Interceptor waits in ambush at L2, other concepts explore faster, more aggressive approaches. Project Lyra, a theoretical study led by the Initiative for Interstellar Studies, examines how to rapidly reach interstellar objects using existing or near-future technology. The challenge is speed. To catch something moving at 26 kilometers like Oumuamua, you need to accelerate your spacecraft to comparable velocities, and you need to do it quickly, months, not years. Conventional chemical rockets aren't enough. Even ion drives, efficient but slow to accelerate, struggle with the timeline. More, you need to do as needed. Seductible. Lyra's solution involves gravity assists and solar orbit maneuver. The idea: launch toward the inner solar system, perform a very close flyby of the Sun, skimming just a few solar radii above the surface, where temperatures are hellish but speeds are maximal, and fire a powerful rocket burn at perihelion. At closest approach to the Sun, the spacecraft is moving at enormous velocity, and every meter per second of thrust translates into larger changes in orbital energy than it would farther out. A leveraging effect that makes the most of limited fuel by combining a deep solar dive with gravity assists from Venus or Jupiter. A fast spacecraft could theoretically be accelerated to 30, 40, even 50 kilometers, enough to catch up to an interstellar object on its way out. The mission would be a sprint, a single high-speed flyby, capturing data in a brief window as the spacecraft screams past at relative velocities of several kilometers per second. It's risky, expensive, and technically demanding, but it's possible, and with advances in heat shields, propulsion, and miniaturized instruments, such missions might become feasible within the next decade or two. Rapid response architectures. Another approach is to develop rapid response spacecraft that can be assembled and launched quickly once a target is identified. Imagine a modular spacecraft design, standardized buses, interchangeable instruments that can be configured in months rather than years, launched on short notice whenever an interesting object is discovered. This requires a shift in how space missions are planned. Traditionally, missions are bespoke, years in development, carefully optimized for a single target. A rapid response architecture trades some optimization for flexibility, accepting slightly lower performance in exchange for the ability to react quickly to opportunities. Rideshare launches, where small spacecraft hitch rides on larger rockets launching for other purposes, could reduce costs. Ça va, Sancho, la, soe, alajtadani. CubeSats and small sats, though limited in capability, could be deployed in constellations, with multiple probes targeting the same object from different trajectories to maximize science return. In situ sampling and what it could tell us. Why go to all this trouble? What would an in situ mission reveal that telescopic observations cannot? The answer is almost everything, in far greater detail. Imaging from kilometers away can resolve surface features, craters, cliffs, jets, layering color variations, revealing the nucleus's shape, structure, and geological history. Spectroscopy in situ samples gas directly, measuring abundances of not just the common molecules but trace species, isotopes, and organic compounds that are invisible or ambiguous in remote observations. Dust collection, flying through the coma and capturing particles on aerogel or foil collectors, brings back physical samples that can be analyzed in laboratories on Earth, revealing mineral compositions, organic chemistry, isotopic signatures, even pre-solar grains if the comet is old enough and pristine enough. Mass spectrometry can measure the exact ratios of isotopes. DH in water, 3Se2C in organics, NN in nitrogen, data that directly constrain formation conditions and compare to solar system norms. For C, vi sägs års. For an interstellar object, these measurements would be transformative, allowing direct comparison between our solar system's chemistry and that of another. Are there jets? Are they steady or pulsating? Is the nucleus intact or fractured? Is the density consistent with solid ice or fluffy aggregate? These questions, which orbital data can only constrain probabilistically, would be answered definitively. Looking ahead, we're at the threshold of a new era in solar system exploration. The discovery rate for interstellar objects is about to explode as next-generation surveys like the Vera Rubin Observatory come online. Comet Interceptor will be ready, waiting at L2, poised to strike. Rapid response architectures are being developed, concepts tested, technologies matured. Within the next decade, it's entirely plausible that we'll have our first close encounter with an interstellar visitor. We'll see its surface, taste its gases, measure its chemistry, and finally, know what these travelers from other stellar systems are truly made of. And when that happens, the gentle speculation of chapters like this will give way to hard data, definitive answers, and undoubtedly new questions that we haven't even thought to ask yet. Beneath the engineering lies the science we yearn for, the chemistry and origins locked in these visitors that we YDE for lots. So it's bot those. Chapter 18. Why it matters. Chemistry, clues and cosmic kitchens. 1200 words. Let's step back for a moment from the technicalities. The orbit fits, the Marsden parameters, the spectroscopy, and ask a simpler, deeper question. Why does any of this matter? Why pour resources and intellect into chasing faint dots of light that will never affect Earth, never threaten us, never offer practical benefit? The answer lies in a truth that's easy to forget in the routines of daily life. We are made of stardust, and comets are the recipe books that tell us how that stardust was assembled into worlds. Every atom in your body heavier than hydrogen was forged in the interior of a star, expelled in a supernova or stellar wind, and incorporated into the molecular cloud that eventually collapsed to form our solar system. That much is well known. But between atoms floating in space and complex chemistry in living organisms is a long story. A story of how simple molecules became complex ones, how ices accumulated into comets and asteroids, how those bodies delivered water and organics to rocky planets. I gaze far, but events. Oh, and how that delivery seeded the conditions for life. Comets are chapters in that story. They're time capsules preserving the chemistry of the early solar system. Or, in the case of interstellar comets, preserving the chemistry of early other solar systems, in cold storage for billions of years, of the years So, when we analyze a comet's composition, we're reading a preserved record of the materials and processes that existed in the protoplanetary disk, the swirling cloud of gas and dust from which planets condense isotopes as fingerprints. One of the most powerful tools in this reading is isotopic analysis. Isotopes are variants of the same element with different numbers of neutrons, chemically almost identical, but with subtle mass differences that cause them to behave slightly differently in physical processes. Deuterium heavy hydrogen is a classic example. The ratio of deuterium to normal hydrogen, DH, is set by the conditions under which water ice formed. In cold, low-temperature environments, deuterium gets preferentially incorporated into water molecules, increasing the DH ratio. In warmer environments, the ratio is lower. Satani to Sazaris. By measuring DH in a comet's water, you can infer the temperature of the region where that ice condensed and compare it to terrestrial water, meteoritic water, and interstellar ice to trace how material moved through the solar system. Carbon isotopes tell a similar story. The ratio 3C2C varies depending on the chemical pathways that formed organic molecules, the temperature, and the presence of specific catalysts. Measuring this ratio in comet organics reveals the chemistry of the protoplanetary disk, where the carbon-rich molecules formed through gas phase reactions in the inner disk, or surface reactions on icy grains in the outer regions. Oxygen isotopes, even more informative. Says no, the even this. The solar system shows a characteristic pattern of oxygen isotopes, slightly different from the interstellar medium average. Measuring oxygen isotopes in a comet can reveal whether its ices formed locally within our solar system, or retained a signature from the parent molecular cloud. For an interstellar comet, isotopic measurements would be a direct comparison to another star system. Do they match solar system values, suggesting universal processes? Or do they differ, hinting at variations in star formation environments, molecular cloud chemistry, or planetary system architectures, organics and prebiotic chemistry? Beyond isotopes, comets carry a staggering diversity of organic molecules, compounds containing carbon, often in complex structures. Amino acids, the building blocks of proteins, have been found in meteorites and are suspected in comets. Sugars, nuclear bases, the components of DNA and RNA, alcohols, ethers, aldehydes. The inventory reads like an organic chemistry textbook. These molecules didn't arise from life. Are the same measures the diseases are that they formed through abiotic processes. Ultraviolet radiation, cosmic rays and chemical reactions on the surfaces of icy grains. But they're precisely the kinds of molecules that life needs. Deliver them to a young planet with liquid water, and you've seeded that planet with the raw materials for biochemistry. Earth almost certainly received such deliveries. Comets and asteroids bombarded the early Earth, carrying water if Earth's original volatiles were lost during formation and organics. Some researchers argue that the prebiotic chemistry that led to life's origin was jump-started by these deliveries, that the first amino acids, the first sugars, the first complex organic molecules on Earth didn't form here, but arrived from space. Interstellar comets extend this question beyond our solar system. If other star systems also produce comets rich in organics, and if those comets can be ejected and wander the galaxy, then organic chemistry, and perhaps the seeds of life, are not tied to single star systems. They're galactic, spread by the slow diffusion of ejected comets across interstellar space. Arbo throughout the study, as are wise as rose. It's even conceivable, though speculative, that a comet from another star system could impact a planet, delivering not just organics, but, if life had formed in that system, even microbial life, freeze-dried and dormant, surviving the journey. This idea, called panspermia, remains controversial and unproven, but it's not impossible. And studying interstellar comets is one way to constrain it. Grain structure and porosity, the physical structure of comet material, also tells a story. High-resolution images from spacecraft missions like Rosetta, which orbited Comet 67b Churyumov-Gerasimenko, revealed a surface covered in fine dust, boulders, and layered terrain. Evidence of gentle accretion, where tiny grains stuck together over time without being compressed or melted. In Dawn Law, the Zen stars. For Ray, porosity measurements, how much empty space exists within the material, reveal how comets formed. High porosity suggests slow, gentle aggregation in the outer disk, where collisions were soft and didn't compact the material. Low porosity might indicate later processing, compression by overburden, or formation in denser regions. For 3I Atlas, if it's a low-density, fluffy object as the radiation pressure scenario suggests, that porosity is direct evidence of how it formed, probably as a loosely bound aggregate in the outer reaches of another star's protoplanetary disk, never subjected to the heat or pressure that would have compacted it into a solid body. Cross-comparison with solar system comets. One of the most exciting aspects of interstellar comet chemistry is the comparison. We've studied dozens of solar system comets in varying detail. We know their DH ratios, their COH2O ratios, their organic inventories. These form a baseline, a portrait of what normal looks like for comets formed around our Sun. When an interstellar comet arrives, every measurement is a test. Does it match the baseline or deviate? So the path so you so we usually or withers of matches suggest universality, that the physics and chemistry of planet formation are similar across different stellar environments. Deviations suggest diversity, that different stars, different disk masses, different distances, different timescales produce different outcomes. 2I Borisov, recall, was broadly similar to solar system comets, suggesting that at least some interstellar visitors come from environments not too different from ours. But one data point is not a trend. We need more. We need dozens, hundreds of measurements, spanning different objects, different compositions, different origins, before we can build a statistical understanding. And that's why each object like 3I Jetless matters so much. It's not just one comet. It's one data point in a distribution that will eventually tell us whether our solar system is typical or unusual, whether the chemistry that led to life on Earth is common or rare, whether the universe is filled with worlds seeded by similar organic inventories, or whether Earth was a unique accident. These are questions that touch the core of our existence, and they're answered gently and patiently, one faint spectrum at a time, one isotope ratio at a time, one distant visitor at a time. If you're curious to help, there are quiet ways to join the watch. Chapter 19. Watching from Home, Citizen Science and Live Ephemerodies. 800 words. Astronomy has always been a science that welcomes participation. You don't need a PhD or access to a mountaintop observatory to contribute. You don't need to understand tensor calculus or quantum mechanics. All you need is curiosity, patience, and in some cases, modest equipment, a computer, an internet connection, or even a small backyard telescope. For objects like 3I Atlas, there are quiet, meaningful ways to join the watch, to contribute to the global effort, and to experience the thrill of tracking a visitor from another star system with your own eyes and instruments. Ephemerodies and sky position. The first step in observing any celestial object is knowing where to look. This is where ephemerides come in, tables that predict an object's position in the sky at specific times. For comets and asteroids, ephemerides are generated by the Minor Planet Center and NASA Jet Propulsion Laboratory, using the best available orbit solutions and updated as new observations refine the trajectory. You can access ephemerides online for free through tools like JPL Horizons system. Ranks groups and Fondsvarsel for Masters. Go. Enter the object's designation. 3I Atlas, for example. Choose your observing location, latitude, longitude, elevation, and the system will output right ascension, declination, altitude, brightness, and other parameters for any date and time you choose. Armed with this information, you can point a telescope, or even binoculars, if the object is bright enough, at the predicted coordinates and search. For faint objects, you'll need patience. Staring at star fields, comparing to charts, looking for the one star that's moved slightly between nights. Use. He. But when you find it, there's a unique thrill. You're seeing, with your own photons, an object that came from beyond the sun's gravitational grasp. Citizen science platforms. If you don't have a telescope, or if observing isn't practical, you can still contribute through citizen science platforms like Zooniverse. Projects there invite volunteers to analyze data, classifying images, marking features, identifying objects that would take professional astronomers years to process alone. Comet observation projects ask volunteers to examine images for signs of Comet, measure brightness, flag unusual features, or track fragment motion. Your classifications feed into databases that researchers use to build light curves, detect outbursts, and monitor activity. It's collaborative science at its best. Thousands of eyes, each contributing a small piece, together assembling a picture no single person could create. Light curves and simple photometry. If you do have a telescope and a decent camera, even a DSLR, you can contribute photometric observations. Varzanet disvambusti, sun, sightance. The process is straightforward. Image the comet, measure its brightness relative to nearby stars of known magnitude, and report the result. Software tools. like AstroImage-J or MaxIMDL automate much of this. You load your images, mark the comet and comparison stars, and the software calculates the comet's magnitude, accounting for exposure time, gain, and other factors. The resulting data point, a magnitude and a timestamp, is then submitted to databases, like the Comet Observation Database (COBS), where it joins observations from around the world. Even simple photometry is valuable. Light curves require dense temporal coverage, and professional observatories can't watch a single comet all night, every night. Amateurs fill the gaps, providing the continuous monitoring that reveals rotation periods, detects outbursts, and tracks long-term trends.
Reporting tips. If you're reporting observations, a few guidelines help ensure your data are useful. Precision matters. Report times in UTC. Positions in standard formats, J2000 equinox, and magnitudes with realistic uncertainties. Calibration is key. Use multiple comparison stars, avoid saturated or trailed images, and note your filter or lack thereof. Unfiltered magnitudes are still useful if reported as such. Context helps. Note seeing conditions, sky brightness, any instrumental issues. This metadata allows others to assess data quality. Be patient. Not every observation will lead to a discovery. And that's fine. Consistency and accuracy over time are more valuable than dramatic results. Community and forums. Online communities. Forums like Cloudy Nights, subreddits like Our Astronomy, mailing lists like the Comet mailing list, connect observers worldwide. You can share your observations, ask questions, learn techniques, and follow the latest discoveries in real time. The community is welcoming, knowledgeable, and always eager to help newcomers find their footing. For 3i Atlas specifically, following the discussion threads, ephemeris updates, and observing reports gives you a front-row seat to the unfolding investigation. You'll see the light curves taking shape, the spectra being analyzed, the debates about what the data mean. And if you contribute your own observations, you become part of that narrative, a co-author in the story of discovery. Astronomy has always been about looking up and wondering. With modern tools and open data, that wondering can be active, participatory, and deeply rewarding. Whether you observe with a telescope, classify images at your laptop, or simply follow along with the latest findings, you're joining a human tradition that stretches back millennia. A tradition of watching the sky and asking, quietly and persistently, what's out there? And so, with community and curiosity, we return to our opening riddle. What does it mean for a comet to act like a spacecraft? This is the wonder we set out to explore, and this is the wonder that 3i/ATLAS offers us. The chance to see that even the smallest forces given time and space can move worlds, that even without intent nature navigates, that even without design elegance emerges, so drift gently like the comet itself into the knowledge that the universe is always teaching, always surprising, always more intricate than we guessed, and know that more visitors are coming, more messengers, more mysteries, more quiet invitations to look up and wonder. The sky is patient, the comets will keep arriving, and we'll be here, watching, measuring, learning, and marveling at the spacecraft that were never built but always flew. Fade to starlight, distant tail streaming, soft piano tones, and rest. So maybe 3i/ATLAS isn't just a comet after all. Maybe it's a message, or a machine, or simply a reminder that our understanding of the universe is still painfully small. Whatever it is, it's moving with purpose now, and that alone should make us wonder what else drifts out there, hidden in the dark, waiting to be noticed. As always, thank you for joining me on this quiet journey. I'm the Sleepy Professor, and here we explore the unknown slowly, carefully, and always with wonder. Until next time, keep watching the silence, because sometimes It's not as empty as it seems.